Hello everyone, this is Abhishek here, and I am back after almost like 2 years. So this is my first video after a long time, and hope you'll enjoy it. And this will be helpful for beginners, maintenance engineers, especially in hydro field, right? So let's begin with some basics. What is the purpose of a maintenance strategy? The purpose of a maintenance strategy is highest availability, serviceability, safety of personnel, and useful life. These are self-explanatory. We need to understand the difference between highest availability and serviceability. Now, just imagine if the shaft has been taken out for an alternator for maintenance, mechanical maintenance. So we shall definitely declare that the machine is out from for a prolonged period of time. So the machine won't be available within a day or two. It may take like 20, 25 days, even a month or so. So we declared that the machine is not available. Now, if the machine is available, but it is out from service for few hours or maybe one day due to some maintenance work, corrective steps, whatever, we say that it is not serviceable at that point of time. So this factor is called serviceability. If the machine is available but we are not able to service the machine, even if we have sufficient input for the prime mover, or we have water level, we have water level is okay for the machine to run the machine, in fact. So now the reasons of failures, these are self-explanatory. You need not I don't require more explanation of this. These are unexpected overloads, temperature excursion, changes in environment, and corrosion in contact surface. Due to thermal heating, there is burnouts and expansion, contraction, leakage of oil. So these are the main reasons of failure. And what do we do in preventive maintenance? We discover the potential faults and we take steps to prevent the faults from developing. Like for example, in a transformer, power transformer, we discover various faults like Buchholz operating, formation of gases. Then we have the winding temperature going high, oil temperature going high. Then the PRV getting operated sometimes, or maybe there is oil leakage from the uh, heat exchanger flanges. So these are the faults, and right? And what are the conditions or the parameters responsible? The ppm in oil, the dissolved gases, moisture, and all those stuff. So we need to work upon that. Uh, if they are above a certain threshold value, we need to take corrective steps. We'll run the circulating conditioning machine or the filtration unit, and or these are the some sort of steps we take. Like, and now what is condition-based maintenance? This is indirect preventive maintenance. What we do is we analyze the data. We take various data, periodic data for the same time and ambient conditions. We do an analysis of those data, whether it's increasing, decreasing. If such data is not available, we do some condition checks. Like, for example, the slip ring brush, uh, the carbon brush we use in a slip ring. We may check the contact force. If the contact force uh, is well within a certain standard value, say 40 kg force, then it's okay. But if it is increased or decreased, then we need to take corrective step. We need to uh, ch uh, change the tension of the brush rocker, etc. And like that. So in condition monitoring, we have condition checking and trend monitoring. We'll come to that. Now, the another way of maintenance strategy is the reliability centered maintenance. We know that equipment performing has certain failure rate, non-zero failure rate, and it is well explained by the bathtub curve. This is a famous curve called the bathtub curve, and this needs to be always as down as possible. If it is down, it is always good. The failure rate is reduced, and you can see that initially there is some larger failure rates, and it decreases and becomes constant. This is a useful life. And after some time, when there is some aging has reached of the equipment, the failure rate reduces. The failure rate increases, sorry, it increases. So the pattern of the curve is like this. So we have certain parameters, simple parameters, maintainability. Maintainability is the probability of having certain downtime within a within a certain period of operating uh, observation. Like operating observer, for example, the equipment is performing for 6 hours and we have a downtime of 45 minutes. So the probability of ensuring 45 minutes downtime in a work period of 6 hours, that is the maintainability. How concrete we are in predicting that this much downtime will occur in a span of 6 hours. That factor is called maintainability. Then another is the mean time between failure. Excuse me. Mean time to repair. These are self-explanatory. Uptime ratio should be high. Mean time between failure and mean time to repair. This is actually a measure of the total time. And mean time between failure is the total time of the equipment running without any flaw. So this is uptime ratio. Uptime ratio should be on the higher side. Downtime ratio should be on the lower side. We need to have lesser mean time to repair, right? And mean time between failure, it should be high. So these parameters are for reliability center maintenance. And when you make the equipment reliable, we need to have more stress on certain aspects so that just the basic maintenance check is not enough. We need to go beyond that and ensure that it performs smoothly, normally, without any hindrance, without any flaw, without any breakdown, unexpected breakdown, undesirable breakdown, leading to outages and loss of revenue, etc. So these are the few examples, simple examples. We know the larger examples like vibration, axial vibration, radial vibrations, going beyond limits and tripping the machine and all. Also deterioration of the excuse me, deterioration of the equipments, and we also know that we have transformer condition-based maintenance packages for transformers like dissolved gas analysis and uh, oil PPM and BDV. These are the smaller examples which are normally overlooked, but it matters a lot, right? So the first one is the carbon brush pressing contact force against lip rings. Just you need to understand that more the contact force beyond the standard value will lead to deterioration of the carbon brush and more carbon dust accumulation, insulation resistance going low, and development of root and earth fault, which is not desirable. Lesser the contact force, what will happen? There will be more sparking, which is again not desirable. Now, next is the cable junction boxes where there is ejection spraying of water. So what happens like in cooling water pumps, water goes into the junction boxes and they lead to short circuit and deterioration of the insulation, right? Because of sparking and all. So this is not desirable. We need to have a check on it. Monitoring is necessary. And if we improve gaskets are available, right? If improved gaskets are available, then uh, we can skip that part also. Monitoring, we can ensure it will ensure that no water goes into it. Then the transmission line insulating this leakage current. Transmission line, what happens? I'll come to that. Leakage current trend monitoring is very essential. If the leakage current continually increases with time, as for a certain ambient conditions and weather, if the leakage current comparatively is increasing, then definitely we need to work on the insulation. We need to work on the switch gears. We need to work on the high voltage insulators and maybe hotline washing, hotline cleaning. And if shutdown is possible, we take a plant shutdown and clean all those switch gears, insulation parts, and whatever way we can ensure that the creepage length is okay, right? Then again, another important feature I have pointed out in power transformers. In power transformers, there's leakage of oil monitored, observed in uh, in flanges in the heat. What do you call it? I think shell type heat exchanger, right? So if you have some spray available which can show the lines of leakage, and if you can check the number of lines, count the number of lines, if the number of lines goes on increasing with time, maybe we can predict that the leakage is increasing more with time. So you may take steps like it may be an indication of increased gas development inside the internal of the transformer. Increased moisture also possible. So you may take corrective steps. These are the small things which matter a lot, We take corrective steps also. We also need to check the trend. We need the condition, whether the condition is deteriorating or not with time. So it's a very effective way of understanding the behavior of the internal part of the transformer. And next one is for the ecosystem condition monitoring of effluent drainage, dewatering with oil content. Oil content in the effluent or the dewatering, that needs to be minimum. We have ensured a separate oil separating unit from oil separating with that needs to extract all oil which goes into the drainage and dewatering sump. So oil content in those drainage and dewatering pits should be low, and we need to ensure because it is harmful for the ecosystem. So some sort of condition monitoring can be done. So this is our role to save the ecosystem also. Then we have some another simple observation is like lubrication and gear oil levels in EOT crane. Then EHB bushing oil levels, periodic monitoring. This one is important. Hot air blower arrangement for for bus duct. Bus duct we have in colder seasons moisture condensing. So we need to have some sort of hot air blower arrangement, which have automatic switching, right? Uh, I have not heard about automatic switching, but maybe we can design something like that, which will ensure that IR is not reduced. If IR is reduced and we still switch on the system, energize the system, then there may be cracks developed in the insulation, support insulators of the hollow conductor. That is not good. And another point is the improved carbon brush dust extractor for insulation resistance uh, uh, improvement. Like if you extract the carbon dust in a proper manner, the rotor earth fault won't be developed. So it is an essential part. In some power projects, I have seen that carbon dust is not extracted properly. So maybe we need to have a proper design of that. So in addition to that, I mentioned some practices, the standard practices, which will ensure that in the lifetime of the powerhouse running operation, there are minimum faults and there is longevity, and the powerhouse runs normally for quite a longer period of time. Normally, the IPPs operate in boot basis. They take over the charge of the powerhouse for nearly 30-35 years. And actually, then it has to be handled in a manner which is in a sound condition to the government and like this. Not necessarily it may be also for lower duration also. So if the practices are good enough, then definitely the operating period of the powerhouse is of for less of uh, will be lesser number of faults and prolonged life of the powerhouse. So the first thing is the standard alignment of rotating equipment, and which will ensure that vibration is well within limits. This is one thing I have understood. Like if the limits are within limits, if the alignment is within limits and well within limits, then maybe we'll have lesser vibrations. And also the designer needs to ensure that there are any there there should not be any flaws. Sometimes there is a faulty design also leads to more of vibration during the running phase. Then the storage procedures and material handling of stator winding components. So normally stator winding components needs to be stored in air-conditioned facility with free from dust. And while handling stator winding components, we need to be very sure that there is no moisture accumulation or dirt accumulation, no formation of air pockets while mixing of resin, and because this may lead to partial discharge during energizing the stator winding. These are some of the observations, small things but matter a lot. And the thing that I have pointed out here is the dust-free environment. We need to ensure dust-free environment assurance in erection stage powerhouse. Dust is a very uh, some sort of uh, not means dust is not preferred in a powerhouse, even if there is dust, because civil works go on and we can have dust in some areas. But if some arrangement is made so that dust does not come in contact with some surfaces which are being cleaned, machine surfaces or mechanical. So at most, what we can do is, at best, we can do is uh, whichever surfaces need to be covered, we should cover it. And whenever it's required, we remove the cover and work on it. This is another way. Very simple topic, simple point, but very effective if practiced. And the most important section for electrical grounding. Grounding is very essential. Proper grounding. Without proper grounding, we can't achieve any standard in a power plant. So we need to follow certain code of practice like NEC, IEC. They are very standard and they have the all the codes necessary in a practical field. So we need to practice all those standards so that we can increase the longevity of the powerhouse. The behavior, the performance of the power system also improves with better grounding techniques, with better grounding and bonding, right? Now, this is an example of trend monitoring. It's just how we can observe. See, I have drawn a load curve of a Rangit Stage 4 hydroelectric project. It's in Sikkim and it was in May 2010. So 7 days were observed. I have plotted all the data into one graph, and you can see various colored lines, and each colored line represents one load curve for a particular day with some maximum demand and all those stuff. There is a certain section here where you can see the curve falls down to 0 kVA. Most likely there would have been any fault or maybe switching off of the main 11 kV switch gear. So comparison is so easier and so much information we can get from trend monitoring. So this is how trend monitoring is done. In another curve, you can see I plotted the line earth current with time. During rainy weather, as you can see here, the line earth current rose up to a very big value, and during the sunny weather, it fell down. So we can compare this part for several days. And if the line earth current, normally we have sunny weather, rainy weather is for a shorter period of time. So we can compare a particular like sunny weather condition for several days. And if the trend goes on rising up, we can perform hotline washing or cleaning of the switch gears after taking a plant shutdown for 5, 6 hours. So this is how trend monitoring is so helpful, right? And and this is a structure of the condition-based maintenance. We initially perform the data analysis. After the data analysis, which has 3 steps: detect, diagnosis, and cure. We have a rough design of the basic structure of the CVM package, right? Then we coordinate with the design department. There is a continuous exchange of information between the two. The power plant client and the original equipment manufacturer also share some drawings and other related information to this block, and they come up with the finalization of the CVM package, CVM design. The CVM design finally hands over uh, its design to the power plant client and OEM. They give some feedback regarding some changes or some queries. Then there is some mutual exchange of information, and finally the design is here. So that much for today. Uh, I think it was helpful, and I'll definitely try to come with a new video shortly. Thank you so much. Thanks for watching.